Hey everyone, this is Dr. Walker. In this video, I'm going to go over the guided example from video 215 on electric potential difference. Let's look at the problem. The problem says a 1 nanocoulomb charge rests as shown. So we've seen this problem before, right? Now we're just asked a few different things. Find the potential difference between points A and B is the first part. So let's tackle this one first. So I want you to think about how you're going to do this. So pause the video, think about what you're going to do. So what was your approach? What equation do you think you're going to use? Right, maybe your first thought was using the equation that the potential difference is a change in potential energy per charge. We'll just farm that equation. However, we don't know anything about the change in potential energy of a charge. So, and remember, we use this equation when a charge is moving through a certain potential difference, and that's not what's happening in part A. Alright, so did you figure it out? What you're going to have to do is you're going to have to find the potential at point A, which is VA, call it that, or little a, and then VB. If you find the potential at 2 points, then the potential difference between the two is just the difference in the two potentials. That's all it is. So potential difference between A and B would just be VB minus VA. All right. So with that in mind, how do we find a potential at a point? Think about what equation that you're going to use. Pause the video. So did you come up with V equals KQ over R? We already found the potential at A in the previous video. So the potential at A, when we plugged in all of these values, it was 899 volts. If you don't remember what values we plugged in Coulomb constant. We're actually going to do it again for VB, so I'll show you what the difference is. We're plugging in Coulomb constant, 8.99 times 10 to the 9. Then the charge that is producing the potential at these points is this 1 nanocoulomb charge. So 1 times 10 to the negative 9. And then we plugged in the distance. So for A, we plugged in the distance of 1 centimeter, which was R equals 0.01 meters for A. We divided by 100 to convert it to meters. So to find a potential at B, the distance from the charge to that point is now to 3 centimeters. So RB is 0.03 meters. So that's the only difference between finding the potential at A versus at B. At B, we are further away, so the potential is less. So we plug in 0.03, and we're going to get 300 volts. So now to find the potential difference between the points, so the delta V, we're going to do VB minus VA, and don't mind these little subscripts here, it's the same potentials. It's going to be 300 minus 899. So it's going to be negative 599 volts. Always make sure that your answer makes sense. Does it make sense that the potential difference is negative? Well, from A to B, you're going to lower potential. So it is a negative potential difference. Let's look at part B. Hopefully, you know which equation is relevant. Think about it. And it's going to be the equation that we mentioned earlier. So part B says the change in potential energy of a proton as it moves from A to B. So we have a charge that is moving from A to B, and we know that there's a potential difference between A and B. So that's when we're going to use this equation. When a charge, little q, is moving through a potential difference delta V, then that charge has a change in energy, whether it's a gain or a loss. So what's happening here is we have a proton, that's our little q, that is moving from A to B. So keep in mind, for this part, this 1 nanocoulomb is not relevant anymore. So it definitely is relevant in the fact that it produced the potential at these points. But now we're looking at the change in energy of a proton as it's moving. So this nanocoulomb charge is stationary, right? It's not moving. This is the charge producing the potential, and the little q, you can also call it big Q, the little q is the one that is moving and experiencing a change in potential energy. So from this equation, we can solve for the change in potential energy by multiplying both sides by q, and we get q times delta V. So what we need to plug in is the charge and the potential difference. We know the potential difference is negative 599 volts. So do you know what the charge is? Can you think of it? Pause the video if you need to. So the charge is a proton. So proton has a charge of E, which is 1.6 times 10 to the negative 19 coulombs. And then the potential difference is negative 599 volts. And that's going to give us the energy in joules. The change in potential energy is going to be negative 9.59 times 10 to the negative 17 joules. So let's think about our answer for a second. The potential energy of the proton decreased, right? It's a negative change in potential energy. Does it make sense? Well, we have a positive charge that is moving away from a positive charge. So that's the direction it naturally wants to go. The potential energy decreases. So it's always good to make sure that your answer makes sense. I hope this was helpful. Any questions, always put them in the comments. And see you next time.